Here we have some more examples for finding probabilities for sample means. A population of values has a normal distribution with mu equaling 150.7 and sigma equaling 75.2. Find the probability that a single randomly selected value is between 145.7 and 155.7. Single value, so just x, so 145.7 and 155.7. You can open up your calculator sheet. So your lower bound is a smaller number because we're looking at in between, so 145.7 and then 155.7. You can plug in your mean of 150.7 and then standard deviation of 75.2. So you should get 0.053. 0.053. Again, mu was 150.7 and sigma was 75.2. B, find the probability that the mean of a sample of size n equals 226 is between those two numbers. So really, what's changing here is that x is now x bar because it's a mean of a sample. The lower and upper bound stays the same. Mu x bar stays the same. Sigma x bar is now sigma over the square root of n, which is 226. When you do that on your calculator, you get 5.00223. So I just go out to 5 decimals. I think that's far enough to get an accurate picture. So really the only thing that's changing is your standard deviation. So update that, you should get 0.6825. You can see that is much different than part A. The birth weight of boy babies of European descent who were delivered at 40 weeks is assumed normally distributed with a mean of 3,687.6 grams with a standard deviation of 410.5 grams. Suppose that there were 9 European descent boy babies born on a given day and the mean birth weight is calculated. Find the distribution of x. So this is the format they wanted in. So x is normally distributed. Your mean, which was 3,687.6, and now we gotta find this standard deviation was 410.5. Okay, what's the distribution of x bar? So x bar is approximately normally distributed. The mean is the same. And remember, sigma x bar is equal to sigma, so 410.5, over the square root of n, and they're 9. So when you do that, you should get 136.83 for sigma x bar. And that 3 is repeating, so you can put a line over it. So 136.83 repeating. That's the distribution. So really it's just what it looks like is the formatting. It just looks a little different, but it's really not too complicated, right? Mu x bar is just equal to your mu. So let's find the probability that the weight of a randomly selected boy. So right away, I'm not seeing mean baby boy, just a randomly selected boy. Probability. That will tell us x was less than 3,500.4. So the good thing about this notation is that we can just use information from part A to figure it out, which we've done before. This is just formally writing it out. Okay, so we have less than, so the lower is -9 because it's less than, and it goes all the way up to 3,504. The mean was 3,687.6 and the standard deviation is 410.5, giving us a probability of 0.3242. 0.3242. Okay. D, find the probability that the mean weight, so mean weight, was less than 3,500.4. Mu x bar, we're going to use what we found here. So 3,687.6, that stays the same. Sigma x bar, 136.83 repeating. So really the only thing that changes here, like we've seen, is the standard deviation. 136.83. 136.0856. Is this unusual? Well, 0.0856 is larger than 0.05, so no. It is not unusual. Let's write this out though. This is not unusual. What we conclude is that there is an 8.6% chance the mean weight of 9 boy babies born of European descent would be less than 3,500.4 grams. Okay. The next question, find the first quartile for the average number of birth weights of boy babies of European descent. Okay, first quartile. Remember, first quartile is the bottom 25%. We are looking for the average weight. That's what we're looking for. We're not looking for probability. So that should indicate number 5 on the calculator sheet. Okay, so we're looking for X is less than, right? Because we're looking at the 25%, the quartile. So we're looking at the first quartile, we're looking at that value. Okay, so let's figure this out. Let's go into the tail. To the left is 25%. We're going to keep these the same because we're talking about the average number. So we need to use sigma x bar here. So 3,595.31. 3,595.31. Okay, we're doing less than because the way this calculator works, it looks at the tail to the left. So just to make it easier on ourselves, that's why we did it. Now, if you wanted to do greater than, you could, but then it would be greater than a value to equal 0.75. So see how it's going to start getting confusing, because greater than, you're looking at the 75%. And then you're going to have to switch it back to 25 because you need the tail to the left. So that's why that's why right off the bat, I did less than, because the calculator looks at less than. So what was the percentage at less than at quartile 1? 25%. So hopefully that explains why I used less than. And then again, remember, you can put in your upper value. Remember, lower will be -9s. Upper value is what we just found. When you do that, you should get 25% or 0.25. Okay, let's look at the next part. Is the assumption of normal necessary? yes, since n is less than 30, remember n was equal to 9, we cannot use the central limit theorem, or CLT. Therefore, it needs to be assumed normally distributed.